Good evening. I will start this journey with a dramatic clip. Please rest assured, nobody was hurt in this clip. So, the theme of this journey is going to be gravity. And gravity matters. If we were able to detect gravity and to detect these changes in gravity, perhaps those two guys would have seen that hole before it actually appeared. So, without any further ado, I will begin my talk about this quantum shadow sensor for gravity. Now, the big G you see there is actually a reason. To be 100% precise, is the UofG. It's a device that was developed at the University of Glasgow, which can detect gravity and is super sensitive. It's a gravimeter, it's a gravimeter. And my job is trying to make this device even better, to make sure that this device can detect smaller and smaller gravitational forces. But how does this device work? So you can see there is an LED shining light on this moving object. And this object goes up and down like a mass on a spring. And it projects a shadow onto a photodetector. The photodetector detects light. But what it actually does, it counts light. And by counting light ending at the two sides of the shadow, it can determine the position of this moving object, and hence the presence of the proverbial elephant in the room. So, allow me to demonstrate for you what I mean by that. If we have a shadow and the shadow moves, we can tell the position of the shadow by looking at how bright the two halves of the field are on each side of the shadow. But when we talk about brightness, when we talk about light, we actually talk about counting light. And how does one go about counting light? It turns out that you count light by counting photons. And what is a photon? So, a photon is that one tiny little spark that appears on a black background. So if you make your light source, like this source is very bright, we make it dimmer and dimmer and dimmer. And the dimmer we make it, the number of photons decreases. Up until at one point, you will get complete darkness. Now, any little amount above this darkness, that little spark, that's one photon. And so this device looks at the presence of a gravitational object around it, which moves the shadow, and by counting the photons at each side of the shadow, we can detect the presence of an object. Okay, so this device now, the way it operates, it uses LED, as I was saying before, and it's really pretty good. It's pretty sensitive, it's pretty accurate. But we can do better than that. And why is that? Because this LED, as it turns out, just spits photons in random positions. So when we try to count the photons at the top and at the bottom, detect the position of this shadow, there is always a bit of random noise associated to it, given by the random positions of these photons. If we were able to see these single photons, they would appear something like this, random dots appearing all over the place. So, if we then try to establish the position of the shadow by counting how many photons end at the top and how many photons end at the bottom, there is always going to be that little noise, this little randomness about the positions of these photons. So my work is about improving this accuracy of determining these gravitational forces. And I plan to do this by using a quantum light source. Now, a quantum light source is a source that uses a very energetic laser that throws these photons, high energy photons, onto a non-linear crystal. It's like a magical crystal. And when these blue photons hit the non-linear crystal, something magical happens. You get twins being generated. And these twins are twins, identical twins, entangled particles of opposite dispositions. If one is happy, the other one is unhappy. If one goes at the top, the other one goes at the bottom. And quantum mechanics ensures that. That always happens. So actually, this is a pretty good thing to determine the position of my shadow, because by design, I will get the same number of photons hitting the top and the bottom. I will be free of this fundamental noise associated with these classical sources. But don't take my word for it. I've got a demonstration here, and for this, I will need two brave members of the audience. Is there anyone that feels brave enough to come up on the stage? Yes, my friend. Anyone else? A girl, perhaps, to keep it diverse and equal. All right. No, there is only space for two of you. Please come on, please come on. All right. So we're going to move this desk. And what's your name, please? Sean, yes. And what's your name, please? Alistair. I'm also a bit dyslexic, so I may forget their names in a while. But Sean, please, you can take that side and you will play for Team Classic. Sorry, Quantum, you see, it's late on the line. And you, my friend, your name is? Alistair, of course. Did he say Alistair right here? Okay. You can take this place, we will place for Team Classical. All right, so the objective here is to fill up the two beakers with exactly the right amount, the same amount of light, classical light in this case, a stream, uncontrolled stream of photons, end up in disordered positions. And in your case, lotus seeds. Are you allergic to lotus seeds? Thank you. Right, so what is going to happen here is, I'm going to give you a signal, and you're going to rush to your protective gear. And we've got latex gloves. So you guys are allergic to latex? Good, that would have wasted one precious minute. And you've got mask, face mask, and you've got your goggles. Always use goggles. All right. And once you've worn all of this safety equipment, you just start, and I've actually asked around, and the safest way of operating this bottle is something like this. But you know, feel free to do it as you like. And so you will try to squirt this bottle inside these beakers, filling them up with just the same amount. And you, Sean, yes, will use the lotus seeds and try to fill up the beakers with exactly the same amount. All right, roll the drums. Begin. I shall then ask for the help of the entire audience to be the judge of this contest. So, we have here photons, these packets of light, discrete packets of light. You should trust me when I tell you that yes, it's the same number in both beakers. And now, let me tell you, what an adventure. There's something strange happening here, I'm not even sure, but we can say that these two don't really look the same, do they? Something went wrong here. You may say it was a rigged experiment. I gotta say, classical team. What do you guys think? All right. So thank you very much. You can either join me on stage or do as you please. Oh yes. All right. So I hope I have convinced you that by using these discrete quantities of light, the estimation of our gravitational force, the estimation of this position of the shadow would be just bang, 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 right on the spot. But let's get back to the real world here. I've been talking about this quantum shadow sensor, about this classical light, about this gravitational forces. Why are these good for us? Why are these good for us in the real world? And I've thought about this. And that's the answer. It's a big thing. It's happening. So you see people now completely taken by this game, right? Walking around with their phones. But with this guy, and with the efforts being made in miniaturizing this device, and with the help of quantum mechanics, we might be able to catch our favorite Pokemons without falling in the hole while using our phone. Thank you very much.